All right, guys, in this video, we're going to be doing some solving and some equilibrium constants. We have a multiple choice and a short answer. So in this one, we've got a reaction. 2NO2 gas will make N2O4 gas. It's a dark brown colorless reaction, colorless on this side, dark brown on this side. Probably doesn't matter for this particular question. And we know it's an exothermic process. Now the question says, a 0.03 mole sample of NO2 is placed in a rigid 1 liter reaction vessel and allowed to reach equilibrium at a certain temperature. What is the value of Kc at this temperature if 0.005 moles of N2O4 is present at equilibrium? So what are we looking for? We want the value of Kc. So first thing I'm going to do is write my Kc expression. That expression is going to be products over reactants. So we're going to have the concentration of N2O4 over NO2 squared. Okay, I get the squared from here, the 2 right there, and then it's products over reactants. Okay, so now I got to figure out those concentrations. So I do know that it started with 0.003 moles of reactant. So that's NO2. And it turned into 0.005 moles of N2O4, and it's at equilibrium. So 0.005 moles is present at equilibrium. So I can't just plug those concentrations or those values. First off, they're moles, but since it's a 1 liter container, we get to assume that they're also the molarity concentration. So we actually have 0.005 molarity and 0.003 molarity, and I just realized I wrote this one wrong. It is 0.03, which is a big difference. Okay. First, I can use this value as this value, the concentration as my products, because that's at equilibrium. So I do know my top number. It's 0.005. And that's in concentration. So that goes good. But I don't know my bottom number. And that's because I don't know how much is at equilibrium. So how can I figure this out? Well, if 0.005 moles was made, I can work backwards using stoichiometry to figure out how much was used up of that 0.03 NO2. And the remaining would be my concentration on the bottom. So I have 0.005 moles of N2O4, and for every 1 mole of N2O4, it required 2 moles of NO2. I get that from the balanced equation. It tells me for every 1 mole of N2O4, I needed 2 moles of NO2. So how much does that mean? I put in my calculator, 2 times 0.005, 0.01 moles of NO2. That's how much was used to make our product, which means I have to take that original 0.03 moles and subtract 0.01 moles from it, which means at equilibrium, there's 0.02 moles of NO2. Turn that into concentration by dividing it by 1 liter. I get 0.02. So the value that goes in here is 0.02. So you do 0.005 divided by 0.02 squared. You plug that in your calculator and you get 12.5. Luckily, that's one of the answer choices, D, and that is the answer. So it's a lot of work just to get that one value. A lot of us are going to want to just take these numbers and plug it straight into your equilibrium expression. You're not going to get the right answer that way. Okay, because that's not the values at equilibrium. Only the 0.005 was. You had to figure out how to convert it to the equilibrium by going 0.03 moles to 0.01 moles and then subtracting it from your original. All right, in this question we've got a graph and it shows the pressures of various times throughout a reaction. And we have 2 questions asked. The first one is, write the expression for the equilibrium constant Kp for this reaction. Okay, first off, let's write this reaction out. That'll be very helpful. And some of us might be wondering, well, how do we know which one's a reactant, which one's a product? Well, you're going to start with reactant always, so you're starting with some stuff, and you should have 0 of the product. So my reaction is SO3 gas. It reaches equilibrium by making SO2 gas and O2 gas. So looking at that, we can write our Kp expression now. Kp. Oh, and I guess I should make note. It needs to be balanced, right? And it does appear to not be balanced. So we're going to have to put a 2 here and a 2 or a, let's see, that's a 2. And this has to also be a 2. And now it's balanced. Okay. All right. I balanced it by balancing the sulfurs on each side, and then the oxygens had to be balanced on each side as well, and they were. So that works out as a 2-2-1. So then I can write my products or my reactants. So I get the pressure of SO2 squared times the pressure of O2 all over the pressure of SO3. And that's going to be squared as well because it's squared because I got a 2 and a 2 here. Products go on top, reactants on bottom. And there is my Kp. Now, part 2 says, what's the value of Kp? Okay, so now we got to figure out what Kp actually is. We got to put in some values. So Kp is going to be equal to, we need to find some values. Now, there's 2 options. Equilibrium is established right here, or it gets reestablished right here. Something happens at T1. So you can use either numbers to solve it, and it will come out both correct as the correct Kp value. I'm just going to use these first ones. So it looks like at equilibrium, there's about 0.5 SO3. So that's 0.5 squared. And then looks like somewhere just under 0.35, so let's go 0.34. 0.34 for my SO2, so that's going to get squared. And then right here, it looks like it's just a bit above the 0.5 line, so I'm going to say it's like 0.7. I'd say 0.17 is going to be where it's at, 0.17 as my final, and then you just plug those numbers in to solve for it. So let me get my calculator out. 0.34 times 0.17 divided by 0.5 squared. And I get a Kp value of approximately 0.079. And in this case, it looks like the units are in atmospheres. So that would be 0.079. Oh, actually, sorry, I lied. This is a Kp value. There's no unit. So it's 0.079 as the Kp, and that's how you would solve that one.